Hi, welcome to this lecture. In this we will continue what we have left in the last lecture, which is we looked at silicon, and now let us see silicon dioxide. Silicon dioxide is an insulating material like any other insulating material like silicon nitride. So, when you talk about the silicon dioxide applications in IC industries varies, right from field oxides to masking oxide to pad oxide to gate oxide to back-end insulators, and there are some native oxides also. This is talk about this native oxide and how to remove those native oxide. That native oxide is nothing but if you have a silicon wafer. So, this is a cross sectional view of a silicon wafer, and there will be a formation of very thin layer of oxide, and this oxide we do not want. This is formed because of the oxygen in our atmosphere, right. So, how to remove this silicon dioxide, which is unwanted silicon dioxide, or what we call is as a native oxide, right. We will see when we look at the lithography process. Then what we call another one is masking oxides or field oxides or gate oxides. Now, again just quickly giving an example of gate oxide. So, we use gate oxide, a thin layer of gate oxide. If you remember the MOSFET, right, a thin layer of gate oxide is used on which the gate is formed. This is SiO2, and we have the source, drain, and gate, right, and we can have a metal, source, drain, gate. If it is p type silicon, we can have n plus source, n plus gate. Gate can be of different thing, can be polysilicon and so on and so forth. But the thin silicon dioxide, thin gate oxide, that is the use of this gate or tunnel layer oxides, and then we can use for the masking also and so on and so forth. So, let us go and understand if we want to remove the silicon dioxide, right. For example, if I have a wafer and on this wafer I have an unwanted silicon dioxide, or just I want to remove even the silicon dioxide that I have grown or deposited. These are different terms that I will use. One I said growing silicon dioxide, depositing silicon dioxide. The growing technique is different, depositing technique is different. Here we have silicon dioxide, and if I want to etch this silicon dioxide, I want to remove silicon dioxide, I can dip this wafer in buffer hydrofluoric acid, BHF. So, in general HF is the etchant for silicon dioxide. You can see here SiO2 will be etched if I dip the wafer in hydrofluoric acid dip. Now, let us understand which are the ways to grow the silicon dioxide, and before that quickly look into this slide, which will also help us to understand how silicon can work as a diffusion mask for common dopants, and what should be the thickness of silicon dioxide when we are going to dope p type or n type material like boron or phosphorus. This can also act as a good diffusion mask for other materials like arsenide and gallium and so on and so forth. So, what I said is a mask, that means that the dopant would not pass through, silicon. So, let us take very quick example. this is silicon wafer. I want to dope phosphorus into this wafer. So, I will pattern the wafer like this, okay, and this is my silicon dioxide. When I dope it with phosphorus, then I should get this N plus heavy doping. Okay. What is this one? Phosphorus. Okay. So, what will happen is, as you can see, this silicon dioxide works as mask. Now, the question is, what should be the thickness of the silicon dioxide? So, to understand what should be the thickness of silicon dioxide, if there is a phosphorus or if there is a boron, we can see this particular plot. Here you can see that depending on the diffusion time, how much time you are diffusing the dopant into the silicon, you can and what is the temperature of the diffusion, you can see the temperature right from 900 degree centigrade all the way to 1200 degree centigrade. This is a diffusion. There are two techniques: pre-deposition and drive in. Pre-deposition and drive in. So, we can look into what should be the thickness of the silicon dioxide when there is a phosphorus or boron that we need to dope, and at what temperature we are doping and how much time we are doping. So, let us take an example of phosphorus, which has to be doped for approximately 1 hour. Then the thickness of silicon dioxide can be determined like this, approximate. That means, it should be 1 micron thick if it is phosphorus at 1200 degree centigrade for 1 hour. Okay. Now, let us take an example of boron. If you want to dope boron for 1200 degree centigrade for 1 hour, then like this, something like this, right. So, for boron, the thickness that is required is 0.1 micrometer, right. All of you should understand 1 micrometer is equal to 1000 nanometer. So, 0.1 micrometer would be how much, right. So, based on that you can calculate how much is the thickness that you require for silicon dioxide, so to used as a dopant masking layer for the dopant. Alright, I hope you understand. Now, let us go to the next one. Just a representative image of how the substrate is used and then dopants are doped. Now, there are two types of silicon dioxide growing technique. One is called, so right now we are focusing on something called thermal oxidation. Thermal oxidation. Thermal oxidations are of two types: dry oxidation and wet oxidation. Thermal oxidation are two types: dry and wet oxidation. Thermal oxidations are of two types: one is dry oxidation and second one is wet oxidation. As the name says thermal, that means it will require a high temperature. high temperature from 900 degree centigrade to 1200 degree centigrade, very high temperature. That is why it is called thermal oxidation. Okay. So, in thermal oxidation, like I said, dry and wet. So, let us see each of those. You can see on the slide the equation for dry oxidation, that is when silicon dioxide reacts with oxygen, it forms silicon wafer which is solid, reacts with oxygen, it forms silicon dioxide. In wet oxidation, what we see is that when silicon reacts with water vapor, it forms silicon dioxide plus 2H2, right. Actually the equation goes like this: silicon plus H2O gives SiO2 plus H2. If you want to balance the equation, you add 2 here, you add 2 here, equation is balanced, and that is why this equation comes. As I told you that both this thermal oxidation technique are at very high temperature, and wet oxidation is about 10 times faster than the dry oxidation, and there are advantages and disadvantages of both of them. The first one is, in dry oxidation you can have a thin film, but excellent insulator. Thin film is about 0.05 to 0.5 microns. Excellent insulator, it is used for gate oxides, for very thin gate oxides, and you can add nitrogen to form oxynitrides. When case of wet oxide, we can use less than 2.5 micron. In practical you will always go for around 2 microns. Is a good insulating material, but not excellent insulating materials. For field oxides or masking oxides, quality suffers. Why is good insulating material not excellent? Because the quality of the oxide layer, it suffers from the diffusion of hydrogen gas that comes out of the film, which creates path that electrons can follow. The room temperature silicon in air creates native oxide, as I told you, very thin, poor insulator, but can impede surface process of silicon. The volume expansion can be given by the equation, as you can see on this particular slide, and if you want to understand what is the thickness of silicon by the thickness of silicon dioxide, you can use this equation. It will come somewhere around the 0.46. This is also available in many books, it is not a big deal, but the point is that what should be the compressive stress of the silicon dioxide when it is formed on silicon versus when silicon nitride is there, how the compressive stress is relieved. So, there are different techniques for that. However, our focus is only on silicon dioxide as of now. Okay. So, what is the next step is that we have to grow the silicon dioxide, and for growing silicon dioxide there are 3 different techniques. These are dry oxidation, wet oxidation, and cryogenic oxidation. So, what are those? So, in dry oxidation, as you can see on this particular slide, so before we go to see the 3 tube horizontal furnace, first let us understand this one. So, this is a furnace. In all cases there are furnaces, right. Here is a furnace, here also and here also, all the technique. This furnace has 3 zone, zone 1, zone 2 and zone 3. Zone 2 has our temperature from 900 degree centigrade to 1200 degree centigrade, whatever temperature may be. Okay. Between 900 and 1200 does not mean it fluctuates, either it is 900 or 1000 or 1100 or 1200. Zone 1 and zone 3 are cooler compared to zone 2. The reason being because when we take the silicon wafer and load the silicon wafers and load this wafer into the chamber, the silicon wafer are at room temperature, which is approximately 25 degree centigrade. From 25 degree centigrade suddenly you expose it to 900 to 1200 degree centigrade, there is a lot of thermal expansion. To reduce that, we first heat it at zone 1, we keep it for some time, then we move to zone 2. After the oxidation is done, we move to zone 3, and after some time you take it out. Alright. So, first the wafer would be here, then after some time you load it here, then after some time you load it here, and then you let the wafer come out. Alright. So, from room temperature back to room temperature, these are different ways of moving it. Okay. The next thing that I want to tell you is the the way the nitrogen and oxygen is utilized. Okay. So, let us see that one, nitrogen and oxygen, the role of nitrogen oxygen for thermal oxidation. So, if you see the first one, let us take for example the dry oxidation. In dry oxidation what we do is, initially nitrogen is on and oxygen is off, and why? Because the oxygen present in the furnace should not react with silicon wafer, because if oxygen is already there, the silicon dioxide starts growing, and that is what we do not want. That is why initially when we load the substrates into the furnace, we keep nitrogen on and oxygen off. Once the wafers reaches the zone 2, like I said, if the 3 zone furnace is there and we kept it for some time, so that all the wafers heats at whatever temperature we have decided, let us say 1000 degree centigrade, right. Then we switch nitrogen off and switch on oxygen, right. This is off, this is oxygen is on, nitrogen is off, so that silicon starts reacting with oxygen to form silicon dioxide. After the process is over, again we switch off oxygen and switch on nitrogen. So, if you steps are like this, nitrogen, oxygen, first step nitrogen on, this is off, this is off, second step when the wafer is inside, when the silicon dioxide is forming or growing, and once it is done, oxygen is shut off, nitrogen is switched on. Okay. Now, with this we can form silicon dioxide, as you know, is a dry oxidation technique. Second oxidation technique is a wet oxidation technique. In wet oxidation technique, what we do is, we have a bubbler. In bubbler you fill H2O, which is water, and bubbler has a heating mantle through which the water will heat and will form water vapor, and we have the water vapor with us. Now, initially again in this case what will happen is, these are through valves, okay, valve 1, valve 2 and valve 3, VALVE, VALVE, valve. So, valve 1, 2 and 3. Initially nitrogen is on, okay, and this nitrogen passes through valve 1. So, valve 1 is on, valve 2 is off, valve 3 is off, and you can load the wafer. Once the and here oxygen is off, okay, when you are loading the wafer. In second step, N2 is off, O2 is on, N2 is off, O2 is on, valve 1 is off, valve 2 is on, valve 3 is on. This is when the silicon reacts with gas, liquid and then solid. Okay. Then in the third step, when you are unloading the wafer, your N2 is again on, O2 is off, valve 1 is on, valve 2 is off, valve 3 is off. Easy. When valve 2 and 3 are on, then the oxygen passes through the bubbler and then only takes the water vapor, right, and water vapor will go inside. That is what it happens in this particular case. This is your wet oxidation technique. Now, let us see the cryogenic oxidation. In cryogenic oxidation, what happens is that initially again same technique, but here we have nitrogen and oxygen and hydrogen separately, and in this case we will mix oxygen with hydrogen for forming H2O, and this H2O will react with silicon to form silicon dioxide. So, in this case, in this particular case, we have O2, H2, N2. When you load the wafer, at that time O2 is off, H2 is off, N2 is on. When the silicon dioxide formation is happening, at that time O2 is on, H2 is on, N2 is off. When you unload the wafer, O2 is off, H2 is off, and N2 is on, right. So, if you use H2 and N2 and wet oxidation using this particular technique, it is much more cleaner than using H2O wafer. So, these are 3 different techniques by which you can grow silicon dioxide on silicon substrate. How the furnace looks like, I will show it to you in this slide, and the furnace looks like this, and here these are 3 tube horizontal furnace with multi zone temperature control. So, there are 3 tubes, okay. At the same time you can use any of the tube or all 3 tubes. This one here is a vertical furnace which is not too popular, horizontal furnace are generally very popular. In this slide you can clearly see that the engineer is loading the wafer into the furnace, and the furnace material or the tubular reactor material is quartz, which is heated by resistance. This is a magnified view here, you can see this very clearly, how wafers are loaded into the furnace. And then as we know that it can be quartz because it has a very high melting point, the furnace, the gas are and the silicon rod is used to push the wafers into the furnace. The way it is loaded is approximately 1 centimeter per second, it is pushed inside the furnace. So, in general the growth techniques of oxidation are gate oxides for MOSFETs, mask oxide which is in fabrication process, and we will be talking about how to use this oxide when we will see the process flow. Filled oxides that can act as an insulating layer in CMOS fabrication, and the application of thermally grown as well as deposit oxides are shown in this particular figure, which you can see it can be a filled oxide, mask oxide, ped oxide, gate oxide, and so on and so forth. Now, once the oxide is ready, right, how to measure the thickness of this oxide, and for that you have a different technique. The first one is called surface profilometer or mechanical thickness measurement. Here suppose I have a silicon wafer, and on silicon wafer I have grown silicon dioxide, and I want to know what is the thickness of silicon dioxide. So, I have a silicon dioxide. Now, you know that when you load the wafer into the furnace, the oxygen will react on both sides of the silicon, right. It is not like up to the scale. So, do not worry, silicon dioxide is 1 micron only compared to silicon, and that is why you can see that silicon is about 450 micrometers, it is not up to the scale. So, if I want to know whether it is 1 micron or not, or what is the thickness of silicon dioxide, what I need to do is something called photolithography, and with photolithography I will be able to etch silicon dioxide, and pattern silicon dioxide like this. Okay, this is silicon dioxide. Now, I will use this stylus, okay, and I will move the stylus from here, and when it comes here, right, there is a step, this step from here to here, right, will determine the thickness of silicon dioxide. Suppose this stylus is here, it has to go here. So, what is the height that a stylus has to be lifted off, so to reach this area, right, here is what determines the thickness of silicon dioxide. In this particular case, you can see stylus moving towards scanning line. This is a destructive technique. Why? Because we are etching silicon dioxide to create certain patterns, and these patterns are used for measuring the thickness of silicon dioxide. This is a mirror image of the stylus in this particular case, which is shown in the photograph, and then there is a UI through which you can control the stylus, and you can know the exact thickness of silicon dioxide. So, let us move to the next way of measuring silicon dioxide. The second way of measuring silicon dioxide is by looking at the color of the silicon dioxide. Now, this is a very crude way of measuring, but as the thickness increases, the color also changes. Why? Because silicon dioxide being a transparent film, the light will pass through it, hit the substrate and will reflect. So, oxide thickness will create a constructive interference, which we can view from the top, and also or I can tell the color difference between two films having 10 nanometer thickness. Once we are used to look at silicon dioxide in the fab for long time, then probably that accuracy of 10 nanometer will come. Otherwise, at least we can say that it is 1 micron or 0.5 micron and so forth. So, this is just like quick measurement of thickness of silicon dioxide. The way better measurement of silicon dioxide can be using the ellipsometer. You can see the figure of ellipsometer in this particular slide or photograph, and the way it works is the light will pass through the filter, it will send to the polarizer through quarter wave plate, it will hit the silicon dioxide thin film material, and the light reflected would be analyzed and will send to the detector, and finally we can understand the thickness. The after the quarter wave plate, when light pass through the quarter wave plate, the linear polarized light becomes circularly polarized, which is incident on oxide cover wafer. The polarized light reflects back, and it depends on thickness of refractive index, which is usually known for the oxide layer and determined to calculate the oxide thickness. Material wavelengths, incident angles can be used to measure thickness, refractive index of each film in a multi-film stack. For example, if there is a silicon dioxide and on silicon dioxide there is silicon nitride, then what is the thickness of silicon dioxide and what thickness of silicon nitride? Both we can determine with the help of the ellipsometer. There is an electrical thickness measurement of the oxide as well. Since we know that silicon dioxide can be deposited on silicon oxide, we can use a small AC voltage on the top of the DC voltage for capacitance measurement. The substrate can be N type, and in this case let us select that it is a N type substrate. An electron is a majority carrier and the hole is a minority carrier. And what happens is there can be accumulation, there can be depletion, or there can be inversion. So, in the accumulations technique, right, what happens is positive gate voltage attracts electrons to the interface, and when depletion technique, negative bias pushes electrons away from the interface. So, no charge at the interface, while inversion further increase negative voltage causes holes to appear at the interface. So, there are different ways by which we can measure the silicon dioxide. This is a capacitive voltage measurement of a MOSFET. From that we know that what is the thickness of silicon dioxide on the silicon. But like I said, there is ellipsometer, there can be just visual measurement, there can be optical, optical profilometer, which is using the stylus or diamond coating. So, this being the last slide, what we have seen in this particular lecture is how the silicon dioxide is grown on silicon wafer using two techniques, of course not two techniques, but thermal oxidation. In that thermal oxidation we have two techniques, dry oxidation and wet oxidation. Further, when we look further into dry oxidation, okay, it is very simple, Si plus O2, but wet oxidation we can use water vapor or separately mix H2 and O2. There is a 3 tube horizontal furnace, there is a single tube horizontal furnace, there can be vertical furnace, horizontal furnace are used often, there will be multiple zones, how the nitrogen oxygen can be operated. So to only form silicon dioxide which is what we require, and not the silicon dioxide which is is formed when we load the substrate. It is not correct. Only when you load the substrate it reaches to right temperature, then let the oxygen flow and let the oxygen react with silicon to form silicon dioxide. Advantages of wet oxidation, advantages of dry oxidation, disadvantages of wet oxidation, limitation of wet oxidation, limitation of dry oxidation, this all comes as a part of this particular lecture. In next lecture we will take the PVD techniques, which are physical vapor deposition techniques, and we see that how we can deposit different materials on a substrate, whether it is a insulating material, semiconductor or metals. Till then you take care, look at these slides, understand it. If you have any question you can always ask us using the forum. Till then you take care, bye for now.